Howdy, cosmology students, and welcome to the next lecture. When I recorded this lecture, it occurred to me that it was going rather long. And then it occurred to me, oh yeah, that's because I'm recording 2 lectures in the space of one. So, this particular lecture is going to end fairly abruptly after I start talking about, or after I'm done talking about Galileo. So, please watch out for that. As for the second half of the lecture, hopefully I can still use part of that for the next lecture that you'll have, which should be posted relatively shortly. This lecture deals with the Copernican revolution. The Copernican revolution is the first time that we see a major paradigm shift within the field of astronomy. It refutes the Aristotelian idea that the humanity, or the Earth more specifically, is the center of all things. And so it shifts us from the center of the universe to but a small offset from the center of the universe. And as we get more into cosmology and further along, we'll find that our position in the center of the universe becomes more and more off center until the meaning of center becomes meaningless. So, without further ado, I hope you enjoy. The next lecture, we will talk about Newton's machine. We will talk about classical mechanics and the formulation of gravity as a force.
Okay, I think we're live, and we're back. Well, I'm live. You're probably not watching this live. No, you're not. You're definitely not watching this live. Anyway, welcome back. And today we're going to be talking about one of my favoriteest things in astronomy, and that is the Copernican revolution. Now, in terms of cosmology, this was the first major paradigm shift in terms of how human beings viewed themselves cosmologically. Prior to this, human beings thought of themselves as the principal agent in the universe. It started with Aristotle, and Aristotle was a brilliant man, and his contributions to physics, astronomy, biology, philosophy cannot be understated. And it really isn't his fault that his arguments were so convincing that they were thought to be indelible for thousands of years. The problem was that Aristotle approached things from a deductive standpoint. He basically had some large overarching views and then forced everything, every physical phenomenon that he observed into that framework. And that framework is simply that the universe is perfect, and by perfect, everything is spherical and unblemished, or at least almost everything is spherical and unblemished. The only exceptions to that would be Earth and the Moon, but those are demonstrably unblemished. Everything works in perfect circles, so everything orbits around everything else in a perfect circle, and as a consequence, it undergoes uniform motion, meaning that an object in space as it moves does not speed up or slow down. It simply has the speed that it has. And so, and first and foremost, it placed humanity at the center of all things. And so the Aristotelian philosophy was the first major geocentric idea or geocentric cosmology that has existed. But before we really get into that, let me click on the right slide. Before we get into that, let's ask ourselves, what exactly did the ancients know? And I will admit to a Western bias here. I will be talking about the ancient Greeks and the Egyptians for the most part. For the Eastern side of things, I have to express a certain amount of ignorance in that, for some reason, the Eastern accounts or Eastern astrological models haven't really survived, or at least have not been If they've not survived, if they have survived, they have not migrated their way over to the Western world. So I apologize in advance for my for that bias. But so what did the ancients know? Well, first off, as I said, the ancients knew that the moon was not an unblemished object. You can see with your naked eye there are gray stains on the surface of the moon. And those are referred to as mare, or Latin for sea, because one of the early hypotheses for what those bodies were in fact large bodies of water, very much like can be seen on the Earth. The other thing that can be seen with the moon, and you've probably all recognized this, even if you haven't recognized that you've recognized it, is that you can see the same face of the moon regardless of the time of year. If you can see the moon regardless of phase, you can see the same part of the moon all the time. So the same face of the moon reveals itself through and conceals itself through its phases. You essentially do not see the opposite side of the moon. You can only see one hemisphere. And this is referred to as synchronous rotation. And what that means from a physical standpoint is that its period of rotation around its period, the amount of time it takes to rotate about its axis, equals the amount of time it takes to orbit around the Earth. And so it presents the same face to the Earth, as can be seen in this diagram, whereas the red is one particular crater and the blue is a crater on the opposite side. You can see as the moon turns, then the red crater is always seen by the Earth, assuming you can see through the sunlight when it's a new moon, and the blue crater can never be seen from someone standing on the Earth. I hope you can see that if the moon, this does not mean that the moon does not rotate. If the moon does not rotate, or did not rotate, then let's take the moon in the new moon phase, where you have the red craters on the left, the blue craters on the right. As the moon went around in its orbit in a counterclockwise direction, that red dot would still be on the left-hand side of the moon. So in the quarter phase, you would see the edge of the red crater and the edge of the blue crater. When it came around towards the full moon side, you would actually see the blue crater and the red crater would be on the opposite side. If the moon did not rotate, you would actually be able to see all of the moon as it orbited around the Earth. It would take 29 days, but you could do it. You could see it. So it's because of the synchronous rotation that we see. So any cosmology that is constructed has to account for this, has to explain why it is we can only see the same face of the moon. Contrary to popular opinion, or some popular opinion, Christopher Columbus, in the age of Christopher Columbus, people did not believe that the Earth was flat. No one really believed that Christopher Columbus was going to sail off the edge of the Earth and die, or disappear. The fact that the Earth has been is a globe has been not only known, but been shown, measured. The radius of the Earth has been measured since around 200 BC, when Eratosthenes did it, with his famous experiments from Alexandria and Syene. He was able to look at the shadow of the sun at solar equinox, or during summer solstice, excuse me, and was able to notice there was a 7-degree angle deviation between where the sun was in Alexandria to the sun and zenith in Syene. And you can see from this diagram that it's a fairly simple, well, probably not back then, but it's a fairly straightforward geometric problem to calculate what the radius of the Earth is given that deviation. And so, and his measurement, as you'll see momentarily, is actually pretty substantial, or pretty accurate given the technology at the time. We are talking 200 BC. The other thing that the Greeks knew, or at least some of the Greeks knew, others weren't so sure about it, but they knew that the sun had to be distant. And Aristarchus was the first person to, Aristarchus of Samos was the first person to make this claim. And what he noticed was that if he took the amount of time it took to go from third quarter to first quarter, that was shorter than the amount of time it took to go from first quarter to third quarter. And the only reason that, or the only geometric scenario where that works out, is if the moon is orbiting around the Earth and the sun is at a very, very distant, very distant away, is very distant from that system, meaning that the Earth-Moon distance is much smaller than the Earth-Sun distance. Aristarchus went even further and basically said that the sun was in fact the center of the solar system. He refuted Aristotle's claim that the Earth was the center of all things. Unfortunately, Aristarchus was thrown out of Athens for having this radical idea. One of the major problems that the heliocentric model had at this time was that they correctly deduced, or correctly inferred, I guess, that if you had the Earth moving around the sun, as opposed to the other way around, if you had the Earth in motion, then if you had a canopy of stars, regardless of whether or not the stars are all at the same distance, or if they're at different distances, if they are at some distance away, but not infinite distance away, then if the Earth is in motion, you should see what is known as stellar parallax. The stars should appear to move with relation to the Earth's position around the sun. They should oscillate backward and forward. Particularly if they're at different distances, then you should see the foreground stars moving left and right far more than more distant stars. This is, like I said, this is referred to as stellar parallax. You can see this from a terrestrial standpoint simply by driving in a car. Objects that are close to the vehicle will be whizzing by, whereas things that are much further away will appear to be moving very slowly or even possibly stationary, depending on how far you're looking away. So because that phenomenon was not observed, the heliocentric idea was rejected. And in a way, this is actually the correct way of doing science. The only problem was, or the hurdle was, that they didn't consider the fact that the stars could be so infinite or so far away, not infinitely far away, but so far away that the parallax is so small with respect to the measuring instruments, that the reason why they weren't seeing parallax wasn't because it wasn't there, but because their instruments were not sensitive enough to actually detect it. But unfortunately, that was the case, and so the heliocentric model was flat out was rejected in favor of the geocentric model. And so here are some of the measurements that, when I say ancient, we're talking about the early Greeks, so around 200 BC to about BCE to around 0 CE. As you can see, the measurement for the Earth's diameter was about was within 10%. The moon's diameter was also within 10%. The sun's diameter was a bit off, but the key thing is that the sun was considered to be a much larger body than the Earth. Even back then, the sun was believed to be much larger than it is now, or much larger than the Earth. Excuse me. The Earth-Moon distance was also within 10%. Aristarchus was able to measure that with fairly good accuracy, simply using geometry. The Sun-Earth distance was off by order of magnitude. Again, they thought Aristarchus thought the Sun was slightly closer to the Earth than it actually is by a factor of 10. But again, doing that measurement, making those measurements, the time measurements. Again, think about this. This was before clocks were a thing, really. He had to come up with, given the, I can't speak today. Given the imprecise nature of the timing, and here we're talking about factors of being off by factors of minutes, radically changes the distance that you get, the Earth-Sun distance. The fact that he was even close, within an order of magnitude, is astonishing to me. So the ancient, so we have known that the Earth is round, that the Sun is distant, and that the solar system is relatively large for a very, very long time. So what did the sky actually tell the ancients? So given this data that they had, what did the ancients, how did the ancients rectify this? Essentially, how did they explain this? Oh, one piece of information that I should point out is something called retrograde motion. So the planets, the word planet comes from the Greek meaning wanderer. So they believe that the planets were objects that were closer than the stars. Maybe they were star-like, they were wandering stars. So it is unclear to me what the prevailing idea behind the physical nature of them were. Did the Greeks believe them to be stars, or did they believe them to be rocky bodies like the Earth? I'm honestly not certain. But they did believe them to be separate objects from the background stars, because they could see them wandering or moving with respect to the background stars, and not in that stellar parallax way that I was talking about earlier. These are moving with their own impetus, with their own motion. One of the things I noticed about that motion was that it was rather peculiar. So they basically noticed that if something is moving from, that stars move from east to west every day. The sun moves from east to west. But the planets moved, for the most part, west to east with respect to the background stars. And they refer to that motion as prograde. That is the normal motion, as it were, because that is the motion that it generally has over the course of the year, or when that particular planet is observable. But occasionally, depending on the planet, you could talk about the order of a few months to even longer, the planet will undergo something called retrograde motion, where the planet will appear to slow down with respect to the background field of stars, stop, change direction, speed up, get brighter, then slow down, get dimmer, stop, and then return to its normal prograde way. So this was a big hurdle for the ancients to come on to jump over, to figure out, all right, how are we going to explain this? And so what they came up with is essentially a merry-go-round kind of situation, where you had, for example, the edge of the merry-go-round was the celestial sphere. This is the construct where all of the stars are located, and this celestial sphere rotates clockwise as viewed from the top, and the Earth is in the center of this merry-go-round, as it were, and the celestial bodies moved counterclockwise to that motion, only slower. So you had a large westward motion of the stars, and a smaller eastward direction with the sun and the moon and the planets. Now, they also knew over the course of a year that the sky changed. The constellations that they could see changed over the course of the year. And this is how they explained that phenomenon as well, is by having the stars move in a western direction faster than the sun is moving in an eastern direction. And so the Greeks developed, Ptolemy specifically, who was a Greek living in Egypt. He developed the first mathematical geocentric model based on this concept. And basically in simple terms, and what I mean by simple terms is that this model, as observations got more sophisticated, or at least became more precise, this model needed to be tweaked over the course of 1,500 years, and it became far more complex. But essentially, what you have is you have the Earth, not quite at the center, as shown by this diagram. This diagram is a little bit off, in that the Earth, even Ptolemy, was not able to rectify the positions of the planets in the sky. He was not able to accurately predict the positions of the planets in the future sky with the Earth at the exact center of the universe. He actually had to offset the Earth from the center. And then surrounding the Earth, for each individual body, so the moon, the sun, planets, whatever, these went around a larger orbit known as a deferent. But in order to account for retrograde motion of planets, planets themselves were on a smaller circular orbit, which orbited around the deferent, and that was called an epicycle. And so, as you can see here, the planet is moving counterclockwise around the epicycle, and the epicycle is then orbiting around the Earth counterclockwise as well. And so to explain the retrograde motion problem, the Greek answer was the planet was literally going in the opposite direction. Because of the way that the epicycle, because of the revolution of the epicycle around the deferent itself, then the planet during retrograde motion was literally closer to the Earth, hence why it was brighter, and it was literally moving in the opposite direction. So it truly was retrograde motion. And this lasted for a really long time. The progress for astronomical observations really didn't progress very quickly, but they did progress, because by the end of this period, by the time of Copernicus, that simple model that I showed remember, there were in the universe, there were the background field of the stars, which were basically thought of to be on a single sphere. Then you had the sun, the moon, each of them on different spheres of their own, and then the 5 visible planets: Mercury, Venus, Mars, Jupiter, and Saturn. Uranus and Neptune were too faint to be seen, and so they weren't known. So you had these 7 bodies all orbiting around. So at the beginning, and each of the planets has not only a deferent but an epicycle. So we're talking, around 9, 10 celestial spheres, depending on how you count it. By the end of this era, it was 66. The number of epicycles needed to accurately predict where a planet was going to be for any given time, you needed 66 of these epicycles in order to get the precision to match with the precision of the observations, the accuracy and precision of the observations that were capable even pre-telescopically, before the telescope. And then Copernicus came along. Nicholas Copernicus was a devout Catholic, and again, not entirely certain, can never really find what prompted him to do this. But he was dissatisfied. We do know that he was dissatisfied with the Ptolemaic model, Ptolemy's model. He was dissatisfied with it. He was dissatisfied, more than likely, with the fact that he had to compute 66 epicycles in order to figure out how the universe worked. And so he came up with a radical idea. He's like, wait a minute, maybe that Aristarchus dude, maybe he was onto something. What if I put the sun at the center of the universe and had everything orbit around that? Can I make a model which can predict the planets equally or better than Ptolemy's in a simpler way? And the answer to that is yes. he came up with the first mathematical heliocentric model that we have record of. And to be honest with you, he was still an Aristotelian in the sense that he still believed things were traveling on perfect circles in perfect uniform motion. So his model wasn't great. It actually wasn't any more predictive than, or any more accurate than the Ptolemaic, but it was far simpler. It still had to use epicycles for a few of the planets, but it was still simpler than Ptolemy's. And it had the added benefit that the Copernican model could accurately predict the ratios between distances. So whereas Ptolemy's model had no idea where any of these bodies were located, the Copernican model could tell you that that the Earth was nearly twice as far away from the Sun as Mercury was. Jupiter is 5 times as far away from the Sun as the Earth is. So the Copernican model could tell you distances, whereas a Ptolemaic model could not. And so this harkens back to the lecture where I talked about Occam's razor. If you have two models that both accurately predict future events to the same sort of precision, then you want to take the second of the two, or the simpler of the two. Now, this didn't kick off very quickly. Actually, Copernicus waited till his near death when he was on his deathbed in order to publish, because he was fearful of the repercussions that people would have, namely the church would have, to this idea that the Earth was no longer prime in the universe, in God's creation, that the Earth was going to be actually taken out of the center of the universe and replaced with the Sun. And so it was many years later that a gentleman by the name of Tycho Brahe, who is perhaps my favoriteest astronomer ever. Oh, I'm sorry, Tycho. I was corrected by a native speaker. It's actually Tycho Brahe. And he's, like I said, he is a fabulous, fabulous dude. If I could meet an astronomer from back in the day, this is the dude I'd party with. This picture that you see here is actually immense. It is a picture of himself that he had painted on the wall of his observatory so that other people could see just how awesome he was. And in a certain sense, he was pretty awesome. He came up with, or he was able to make observations of stellar positions, and what I mean by stellar is basically anything in the sky. He was able to come up with stellar positions with an accuracy of 1 arc minute. He could tell you where anything was in the sky to a precision of 1 arc minute, or 1/30th of the diameter of the full moon. That is unprecedented. Hipparchus couldn't do it. None of the other previous naked eye observers could do it. He had the most accurate accounting of where everything was in the sky at that time, including planets. Now, the reason why Tycho had these observations was because of Copernicus's work, thinking of new cosmologies was sort of in vogue, and so Tycho really wanted to build his own cosmology, and he ultimately did. It's kind of this weird amalgamation between geocentrism and heliocentrism. Everything, to his answer, was everything orbited around the sun except the Earth, and everything that orbited around the sun orbited around us, and so it was just a weird hybrid mess. Tycho was a great observer. As a theorist, he left something to be desired. And so here, I have to admit, this slide is a little out of order. This is the stellar parallax that I was talking about before. We will come back to stellar parallax in more depth later on when we start talking about the cosmic distance ladder and the rungs. Talking about Tycho brings us to Kepler. Now, Tycho. I'm still not quite getting the name right. Talking about Tycho gets us to Kepler. So, Tycho recognized that mathematics was not exactly his forte, and so he, in today's parlance, he hired a postdoc. He hired a mathematician to essentially work out his cosmology for him. And Kepler did that, but Kepler was not happy with the Tycho, I guess the Brahean cosmology, because he fought. Actually, he literally stole the data and then fought Tycho's family in court in order to keep Tycho's data to complete his work. And it took a number of years for Kepler to basically come up with his 3 laws of planetary motion, which were radically different from the Aristotelian. It basically took the Aristotelian model and chucked it. Said, none of this is right. So his first law, and probably his most dramatic from a philosophical point of view, was that orbits are ellipses, not circles. The universe, and so in that one law, he is stating that the universe is not, quote unquote, perfect. It does not orbit around in nice, orderly circles. The consequence of this law is that the sun is at one focus, and there is nothing, despite what conspiracy theorists might have you believe, there is nothing at the other focus. It's simply empty space. And I'll show you what a focus is in a moment. The second law, otherwise known as equal areas and equal times, means that not only do planets not orbit in perfect circles, they don't orbit at a perfect speed or a uniform speed. They change, their speeds change over time depending on their location in the orbit. If a planet is close to the sun, it is going to be moving much faster than if the planet is far away from the sun. So the planet's speed changes with respect to time. The third is the harmonic law, and that is the famous p squared equals a cubed relationship. And what this indicates is that the larger the orbit of the planet, the slower that planet orbits. So again, so not only do the planets not move at a constant speed, they all move at different speeds. So there is no preferential speed or motion in the solar system. So here's an example of Kepler's first law. You can see that you have, it's basically an ellipse is just a squash circle. So you have, instead of a center where you draw the curve around that center, you have instead the center is split into 2 points called foci, or 2 individual focuses. And that leads us to something known as eccentricity. So if you have an eccentricity of 0, then you have a perfect circle. But if the eccentricity, or squashedness, very technical term, is slightly above 0, then you have an ellipse. So as you can see here, 0.5, you have a reasonably oval shape. 0.9, you have a very ovular shape. And then 0.99, you have something that's almost akin to a line. The eccentricity will never equal to 1. That actually gets into a parabolic shape. But point of the whole thing is the orbits of planets moving around the sun. So again, if I hadn't already mentioned it, Kepler set the sun at the center of the universe. Planets are orbiting around the sun in ellipses, such that all of the planets have orbits that have eccentricities just slightly more than 0. Not a whole lot more than 0, only to about 10% or less, but they were definitely non-zero. Kepler's second law, equal areas and equal times. And so there are 2 specific positions on this orbit that you should be aware of. So if you draw a line from the center of the ellipse through the sun to the orbit opposite the sun from the center, that position is called perihelion, or the point closest to the sun. If you go backwards along that line, so you go from perihelion straight through the sun, straight through the center to the other focus to back to the orbit, that point is at aphelion, or is called aphelion, and that is the point furthest away from the sun. So perihelion and aphelion are opposite sides of the orbit, opposite sides of the sun. One is where the planet is going to be the closest, one is where the planet is going to be the furthest away. And what Kepler was able to see was that, given the observation specifically of Mars, he saw that when Mars was closer to the sun, it swept out an larger area, it swept out an equal area than it did when it's further away. What I'm really trying to say is the angle that it swept out was larger between C and D when it was close to perihelion than when it was at A and B, close to aphelion. The angle that was swept out in the sky, it literally traveled faster across the sky during the perihelion visit than it did near aphelion, which told him that because the areas were equal, it told him that the planet moved faster when it was closer to the sun than further away. And this is a consequence of the conservation of angular momentum. And then finally, you have Kepler's harmonic law, p squared equals a cubed. Actually, to be perfectly valid, Kepler was not able to determine he could calculate what the periods of the planets were that he could observe fairly easily. He just basically waited until they came back to the same part of the night sky. The positions, however, he did not know in absolute. He didn't know that, for example, that Mercury was 0.4 AU from the sun, because he didn't know what an AU was. That wouldn't come for another 100 years or so. But what he could do was determine the ratios of things, very much like Copernicus was able to do. Kepler was able to do in a better way, and he realized that the ratio of distances between planets cubed was equal to the ratio of the period of the orbit squared. So not only was he able to calculate that ratio, but he recognized that it was commensurate to another characteristic of the orbit, that the period and this period of the orbit and the size of the orbit were correlated. Then came around Galileo, probably my second favoritist astronomer of all time, physicist of all time. And around 1610, Galileo took a telescope. He did not invent the telescope, again, contrary to some popular opinion. Hans Lippershey more than likely invented the telescope. But Galileo was the first person of record to observe the night sky, or observe heavenly bodies with the telescope, and subsequently write down his observations and publish them. And the four major observations that he made by 1610 was he noticed that Venus went through phases very much like the moon, and he went through phases inconsistent with the Ptolemaic model. So while a certain version of the geocentric model can produce observed phases in Venus, the phases that we actually see are not what would be predicted by said geocentric model. He saw that that there were stars, bright spots on either side of Jupiter that oscillated backwards and forwards given over time, and he correctly deduced that these four bright objects, now known as the Galilean moons, were bodies which were which were bound. He didn't know about gravity at this point yet. Four bodies which are tied to Jupiter somehow, that they were oscillating back and forth in orbits in and upon themselves. And this flew into, so the first point, phases of Venus, again, flew in the face of the perfect spheres from the Aristotelian philosophy. it showed that not only the moon goes through phases, but also Venus does as well. So not everything in the universe is perfect. Moons of Jupiter illustrated that regardless of the Earth being at the center, the Sun being at the center, this illustrated that there were that things could orbit bodies other than the Earth. So the Earth again was not primary in cosmology. There was basically something that was akin to the Earth in the observable universe. He observed mountains on the moon. Now, while the gray stains it was okay to think of them as bodies of water, the idea that the moon had any sort of topography, again, was in rejection to the Aristotelian philosophy that things were unblemished. While bodies of water were okay, apparently mountains were not. And so that was a revolutionary or a big point of contention during that time. And then finally, sunspots. Again, blemishes on a perfect heavenly body. These are dark spots on the surface of the sun. Galileo was actually able to not only observe them by projection, he projected the sun's light through the telescope onto a sheet of paper. He noticed those spots existed, and he was able to watch them over time. He determined that the sun actually rotated around an axis, and he saw that the spots changed shape based on where they were on, where they appeared to be on the sun's surface, which meant that they were not intervening clouds, that they were objects that were on the surface of the sun as opposed to between the Earth and the sun, just blocking out light. So here we see that what Galileo actually observed was, again, the Venus went through phases. Venus was never seen in a full phase, as you can probably guess. The reason for that is the sun was in the way. Venus is never seen in the new phase. That should be fairly obvious as to why. But when Venus grew, or when Venus went from a gibbous phase to a half phase to a crescent, Venus got noticeably larger in extent. Not noticeably brighter, but definitely noticeably larger. And as you can see, the alpha indicates the angle. So it basically grew to 3 times its size, going from a gibbous phase to a crescent phase. That was in opposition to what the geocentric model would have predicted. In fact, the geocentric model would have had the Venus getting much larger in gibbous than it would be in crescent phases. Here are some actual observations of Venus that illustrate this principle. And again, here is the actual Ptolemaic model, where in order for the Venusian phases to be explained, he had to make it even more kludgy by basically saying that the deferent of Venus and the deferent of the Sun had the same angular velocity. No other planets did. No other planets were tied to the Sun as Venus was. But that was the only way that Ptolemy could even explain that Venus could go through any kind of phases. And again, the phases really didn't match up. The size of the planet did not match up with its predicted phase. Here are Galileo's notes in terms of the moons of Jupiter. You can see the asterisks are the moons as you can see them, and then this is the date. You see that the stars or the moons oscillate from left to right over time, and he was correctly able to deduce that these were smaller bodies, in fact, orbiting around the planet.